Hi, everybody. We are now going to get into one of my favorite topics for a first semester biochemistry class, and that is enzyme inhibition. Enzyme inhibition to me is absolutely fantastic because there are some unique models that we look at. In addition to that, there are some graphs that, well, if you can keep these graphs straight, then I think that an understanding of the graphs and an understanding of the models for inhibition, they kind of feed into one another. So I always kind of look at this as if you struggle to understand the models, work on understanding the graphs because understanding the graphs can support an understanding of the models. Um, I think that this is just a really fascinating and cool thing to study. And so this is our topic, enzymes and enzyme inhibition patterns. So, enzyme inhibitors act in a variety of mechanisms. An inhibitor may bind at the same site as one of the substrates. So, what we're doing is we're kind of visualizing that we have an enzyme. Why is it doing that lately? Okay, so we've got an enzyme, and then we have our substrate, and then we've got an inhibitor. Okay, so I've drawn this substrate to look kind of like it can fit right in there, and then this inhibitor also looks like it could fit in there. All right, now these inhibitors, so as I've drawn these two simple models, um, this sort of inhibitor structurally resembles the substrate. Now, what that could mean is that the difference between them is as simple as like a methyl group or something like that. But structurally, they're going to look fairly similar to one another. An inhibitor may bind at an alternative site, affecting catalytic activity without affecting substrate binding. Now, this would be a sort of inhibitor that, well, here's another model for an inhibitor. So I'm going to call this inhibitor 1, inhibitor 2. And maybe this inhibitor 2, what it does is it binds to this surface of my enzyme and alters it from kind of a different angle. Now, there are also inhibitors that do both. So they bind at the active site and they resemble a substrate, but then they also bind somewhere else. Now, one of the things that I kind of caution you, not necessarily against, but caution you on is when it comes to a discussion of enzyme inhibitors, I think that there's a temptation to say, okay, well, we've got these different models, but what type of inhibitor is the best? And that to me is kind of like, well, you have multiple different methods and strategies to solve a problem. I always kind of think about it almost like not necessarily preference, but um, let's say that you have a math problem that's like 312,522 plus 6,417. It might be easier for you to write that number down or write those two numbers down and just add them up. Whereas a calculation like 3,642,758 times 9,417. That's a number or that's a calculation that's a little bit more complicated, and it might be better to use the calculator. Now, my point is that you have a tool, a calculator, and it might just be easier. It might make more sense to use that calculator in some instances, and then it might make more sense to use just the pen and paper in another example. So when it comes to these sorts of calculations, it's or sorry, when it comes to these sorts of models, you shouldn't necessarily look at it as one type of inhibitor is better than the other, but I think that it's more beneficial for you to look at it as, okay, this type of inhibitor is effective in this specific reaction. This type of inhibitor is more effective in this type of reaction. So we will discuss multiple different inhibition patterns because they all have value and they all bring something different to the table. Now, our most common types of inhibitors are competitive, mixed or non-competitive, and uncompetitive. Now, these different types of inhibitors, they're going to follow some simple patterns, and I think that they're pretty good to get a, or they're pretty easy to get a good understanding of. But this is a PowerPoint that I strongly recommend that you go back through multiple times. Now, before we get ahead of ourselves, all of these types of inhibitors are classified as reversible. And as reversible inhibitors, they're going to be utilizing or kind of exploiting or, let's see, not exploiting, but they are going to uh, interact with our enzyme through non-covalent interactions. So these are going to go through non-covalent interactions. So lots of your um, weak interactions, hydrogen bonds, ionic interactions, intermolecular forces. That's how these are going to be mediated, as opposed to an irreversible inhibitor, which is something where you're going to alter covalent bonds. Okay, so inhibition patterns. This first type of inhibitor, known as a competitive inhibitor, competes with the substrate for the enzyme, specifically the substrate binding site. Now, if we bounce back, an inhibitor may bind at the same site as one of the substrates. This is a competitive inhibitor. Okay. Now, this notation right here, E, S, E, S, P, E, we've seen that before, and this is known as the Cleland notation. Using the Cleland notation, our enzyme can, given the opportunity to, it can bind to the substrate. It can then form the enzyme substrate complex. So in the event that our enzyme binds to our substrate, we should expect to see the enzyme substrate complex form. When the enzyme substrate complex form, then we're going to go ahead and we're going to convert that into our product and our free enzyme. Now, this, just imagine that all of this right here is almost in one beaker. Your enzyme, your substrate, and your inhibitor are all in the same container. So it's not necessarily flipping a coin, but your enzyme has basically an equal opportunity to bind the substrate or the inhibitor. Now, of course, that's going to vary based on the concentration of the substrate or the inhibitor. But let's imagine that our enzyme has an equal affinity for our substrate as it has for its inhibitor. Then we'll form that ES complex or the EI complex in the event that, let's say, our enzyme has a greater affinity for our inhibitor. If either the inhibitor is at a higher concentration than the substrate, or the enzyme has a preference to bind the inhibitor, then that EI complex is going to form. So when we look at this, and we have the enzyme substrate or the enzyme inhibitor, we've got almost an equal possibility of the EI or the ES complex forming. Now, one thing that is not going to form is we are not going to see the enzyme substrate and the inhibitor form one complete complex. So I'm going to write out here ESI, and I'm going to circle that and say, no, that complex, that three-component complex will not form. Now, our next type of inhibitor is referred to as an uncompetitive inhibitor. Now, this language gets a little bit tricky but I want you to be patient with yourself and with this language. So an uncompetitive inhibitor binds to the enzyme substrate complex, but not to the free enzyme. It binds to the enzyme substrate complex. So what that means is ES versus E. An uncompetitive inhibitor can bind to this. It cannot bind to simply the free enzyme. So it has no affinity for the enzyme, and seemingly it has no affinity for just the substrate. So instead, it is looking for that ES complex, and it's looking to bind to that ES complex. And the way that is displayed with this Cleland notation is E plus S yields ES. That enzyme substrate complex will absolutely form with an uncompetitive inhibitor present. What the fate of that is, however, is this ES can basically be almost rerouted to form this ESI complex. Now, if that ESI complex forms, no reaction is going to take place. So if the ES complex forms, there's a chance that your product's going to be made. There's also a chance that your inhibitor is going to bind and you're going to form the ESI complex. Now, what I always like to do whenever I'm looking at my different types of inhibition is take stock of what can form and what cannot form. With the uncompetitive inhibitor, EI will not form. We will not get the enzyme inhibitor complex to form in the presence of an uncompetitive inhibitor. Now, our next type of inhibitor is a mixed inhibitor. A mixed inhibitor is a type of inhibitor that can bind to the free enzyme and the ES complex. So let's go ahead and draw a line there and show what that looks like. Now, this is the type of inhibitor that I think, if actually, typically when people hear about a competitive inhibitor, they think, perfect, it's going to compete with the inhibitor and it's going to block the inhibitor from binding to the free enzyme. Awesome, that's what I'm looking for. Then they hear about the mixed inhibitor and they think, well, this inhibitor, it sounds like it's kind of a two-pronged approach. It's almost an improvement on a competitive inhibitor. It's almost an improvement on an uncompetitive inhibitor. So is that mixed inhibitor the best type of inhibitor? Now, I say that just to really bring up and caution you against thinking what type of inhibition is good or bad or anything like that. Do not think about, well, this is the best type of inhibitor. Instead, think about it as the basically what the inhibitor can possibly do. In the case of a mixed inhibitor, ESI can form. So I'll put a circle around that. In the case of a mixed inhibitor, EI can form. So a mixed inhibitor effectively does the opposite, or does what a mixed inhibitor and an uncompetitive inhibitor do kind of in combination with one another. So these are the different models and the major types of inhibition that you need to be familiar with. Understand the complexes that can form, understand the fate of the different complexes, and if they form or don't form. I always like to look at it like this and say competitive, ESI does not form. Uncompetitive, EI does not form. Mixed, EI and ESI will both form. Now, with that said, how do we distinguish between these different types? Well, what we need to do is make an inhibition plot. This is very similar to an initial velocity plot, but we're going to use an inhibitor instead of a second substrate. So what we can get from this is we can get a pattern or the pattern that formed determines the type of inhibition. Now, what we're going to do here is we're going to, well, just a second. Let me backtrack for just a second. When we talk about an inhibition plot, I want to bring back the graphs that we've talked about. We've talked about a graph that looks like this, initial velocity versus substrate concentration. That's our Michaelis-Menten plot. Then we have a Lineweaver-Burk plot, which is also known as a double reciprocal plot, which I'll label as a DR plot. And that DR, or double reciprocal plot, is 1 over initial velocity, and our x-axis 1 over substrate concentration. This Lineweaver-Burk or double reciprocal plot is the type of plot that you're going to be, or you're going to need to be most familiar with for the study of different types of inhibitors. Can inhibition data be plotted on a Michaelis-Menten plot? 100%. Yeah, no doubt about it. Is it, I would say it's most typically plotted on a Lineweaver-Burk plot, though. So just keep that in mind. Now, let's go into the different types of inhibition and see what this looks like on those different plots. A competitive inhibitor competes with a substrate for the enzyme substrate binding site. So basically, where that substrate's supposed to go, a competitive inhibitor kind of slides in there and says, nope, not so fast. So as an example, if you remember from this slide right here, one of the hallmarks of a competitive inhibitor is that they structurally resemble the substrate. So they look a lot like the substrate. Here's an enzyme known as succinate dehydrogenase. This is an oxidoreductase. This oxidoreductase enzyme takes an enzyme like succinate and converts it to fumarate. This does an oxidation reduction reaction where basically we're putting a double bond right here. Okay. Now, succinate dehydrogenase is an enzyme that is inhibited by a molecule known as malonate. Okay, let's look at succinate. 1, 2, 3, 4 carbons. Okay, it's got a carbon backbone. Malonate is 1, 2, 3 carbons as the backbone. Now, carbons 1 and 4 are carboxylate ions. Carbon 1 and 3 are carboxylate ions. Now, malonate is going to inhibit succinate dehydrogenase. Succinate is the preferred substrate of succinate dehydrogenase. So structurally, these are very similar. Succinate and malonate, what's the difference? CH2. One carbon is the difference between the size, well, 1 carbon and 2 hydrogens is the difference in size between malonate and succinate. Malonate is a competitive inhibitor because it basically resembles that substrate and is able to bind there, but then kind of prevents succinate from binding. Now, the way that this malonate and any other competitive inhibitor is going to work is if we have, let's put it simple, and let's say that our enzyme has an equal affinity, so an equal chance of binding the substrate and the inhibitor. It's almost flipping a coin. If you have one copy of the substrate present and one copy of the inhibitor present, well, then it is just flipping a coin. And it's a matter of, well, there's a chance I bind the substrate, there's an equal chance that I bind the inhibitor. If I bind the inhibitor, then EI forms. If I bind the substrate, ES forms. Now, a competitive inhibitor is going to reduce the amount of free enzyme available for substrate binding. That's going to lead to an increase in the Km for the substrate. So essentially, it's going to give you this illusion that the enzymes, so increasing the Km, the enzymes, I'm just going to label it as E's, affinity for S goes down. Because the Km goes up, the affinity for the substrate goes down. Now, one of the things that you can do in order to combat that, basically, combat a competitive inhibitor, is, well, remember our enzyme has an equal chance of binding the substrate and the inhibitor. What if you put more substrate in there? Well, then now all of a sudden it's not 50-50. Instead, it's like you got, let's see, that's 6 copies of the substrate, 1 copy of the inhibitor. That's you've got a 1 in 7 chance of binding the inhibitor, whereas you've got a 6 of 7 chance of binding the substrate. So essentially, you increase substrate concentration to outcompete the inhibitor. I'm just going to leave that as I. The effect of a competitive inhibitor can be overcome with high concentrations of the substrate. Now, this is something that is observed and exhibited in vitro as well as in vivo. A cell can overproduce something, and it's almost like, uh-oh, we're in trouble. This enzyme's not working. Well, let's make more of the substrate, more of the substrate. Okay, that's going to offset the impacts of this competitive inhibitor. Now, the way that this is going to be displayed with this Michaelis-Menten plot right here and our double reciprocal plot here, it's going to be displayed in a couple of different ways. Here, what I'd like you to do is focus on the Michaelis-Menten plot. We have a total of 1, 2, 3 different studies with an inhibitor present. Now, in this first line right here, the one that's kind of olive colored, there's no inhibitor present. And what's going to happen to this curve is it's going to basically rise, 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 and then it's going to plateau right around where we see our Vmax. Now, let's look at our next line, this alpha equals 2. Well, what we're going to see is this line's going to increase, and it will eventually get to the exact same Vmax. What's it going to take? It's going to take so much more of your substrate. Increase that substrate concentration into eternity, and you will finally get there. Same with alpha equals 4. What this means is that with a comp inhibitor, Vmax will be reached. You will get there. You will get there. It just takes a huge amount of the substrate. Okay, so now let's think about this. If you remember our Km, Km is the substrate concentration that we're going to need to reach half of Vmax. Okay, so let's imagine that this line right here, that's half of our Vmax. What does our olive line show us? It shows us that we need that. Yeah, Km, that's the quantity. Let's go ahead and I'm going to change these from multiples of Km. I'm going to give them like real numbers. Let's go with 5, 10, 15, 20, 25. And this would be millimolar of your substrate. So that's my x-axis. Okay, so this line right here shows me what I need to coordinate my y-axis, my Vmax over 2, to my x-axis. So this alpha equals 1. Alpha equals 1. My Km equals 5 millimolar of my substrate. So I need 5 millimolar of my substrate to reach half of my Vmax. Okay. Now, the next line, or the next point, when alpha equals 2, right here, well, at alpha equals 2, I needed to coordinate and figure out where Vmax divided by 2 is. And I got to do that line, dashed line to coordinate to, well, alpha equals 2, Km equals 10 millimolar of my substrate concentration. So what happened to my Km between no inhibitor and let's just call it 1 millimolar inhibitor? Doesn't matter. What does matter, however, is that I have a fixed amount of my inhibitor. This line right here, so all these little dots that make up this trend line, those correspond to experimental trials where there is a fixed amount of an inhibitor. So my Km went up. My Km goes up with the addition of the inhibitor. Then for this last line, alpha equals 4. Well, that is Km equals, oh boy, that's right about there. I'm going to call that 17.5 millimolar substrate concentration. Okay, so what that means is that I had to have a lot of my substrate present in order to get this protein, or in order to get to my Km. So my Km went up again. Do I still reach the same Vmax? I absolutely do. Okay, so one thing that I was just saying was when we look at inhibition, we're typically going to look at a double reciprocal plot, which is why we've got a double reciprocal plot down here. This data set right here is this same data set, but it's the reciprocal of your y and your x values. Now, what you notice about this is that my x-intercepts here, here, and here, they are different. Why is that? Well, let's see. Blue line is no inhibitor present. Green line is plus some inhibitor. Magenta line is plus 2 times the inhibitor from the previous trial. As I've increased my inhibitor concentration, my x-intercept goes down. It goes from -5, -3, -1. Now, I understand that you might be thinking about that. Well, -5, is that a larger or smaller number than -1? I just mean it gets closer to 0. Mathematically, that probably doesn't jive. But what I'm meaning is that my x-intercept is getting closer to 0. Now, the significance of this, well, remember, my x-intercept, whether if it's -5 equals -1 over Km, -3 equals -1 over Km, -1 equals -1 over Km. What happens to my Km? My Km equals 1 divided by 5, which is 0.2. Km equals 0.33. Km equals 1. What happens to my Km? It goes up, which is exactly what we saw with this other plot. But it's a little bit easier to quantitate because we can look at that x-intercept here, here, and here and plug those values in. The next value that we want to look at is my y-intercept. My y-intercept, for all three of those lines, what happens to it? You're right. It doesn't change because my Vmax does not change. Okay. So when we talk about Km, Km is a measure of affinity for our substrate. Ki is basically the inhibitor's affinity, or the affinity that your enzyme has for the affinity, the inhibitor. Now, there are two ways to calculate Ki. What you need to do is, and what I would recommend doing, easiest one to me, is this one right here. You take the concentration of your inhibitor, I, and you divide it by a ratio of your Km with the inhibitor and without the inhibitor -1. So that's this part 1 right here. Part 2, calculate the slope with and without the inhibitor present. And that's right here. Now, effectively, what this gives you a way to do is measure the affinity that your enzyme has for that inhibitor. You can calculate this, and just like a Km, the lower the value, the greater the affinity. Another way that you can look at these Kms, these different Kms, is Km plus the inhibitor is referred to commonly as the Km apparent. Km without the inhibitor, well, it is just that. It is referred to as your Km. Our next model for inhibition. Now let's bounce back for a second before we get to this. going back to this slide right here. Uncompetitive. Uncompetitive inhibitor binds to the enzyme substrate complex, but not to the free enzyme. Okay, so EI is not going to form. So what should we expect? Well, one thing that's worth expecting is that our substrate, we can't do, like, the substrate's binding. The question is, what is done with that enzyme substrate complex? So let's move forward. Let's go back to this slide right here. Uncompetitive inhibitor or uncompetitive inhibition. The ESI or EIS complex is going to form. EI is not going to form. An uncompetitive inhibitor binds to the enzyme substrate complex, but not to the free enzyme. So that to me sounds like, or the way that I always kind of visualize this is I've got my enzyme and here's my substrate. And then this cleft right here is where my inhibitor is going to bind. That inhibitor is going to bind only when the enzyme and the substrate are interacting with one another. Because if we look at it as this, this kind of contour, this groove right here and here, well, they might only be present when the substrate's present. So this is a site that basically is not present without the substrate being present. Now, the result of this is a decrease, so a lowering of Vmax. Okay, let's talk about Vmax. So Vmax, to me, if you lower the Vmax, that's almost like, oh, well, my Ferrari did have a maximum velocity of 160 miles per hour, but it drops. So now it's 140 miles per hour. Okay, got it. Makes sense. It cannot go as fast as it once could. Okay. Now, Km. Let's talk about that. When Km goes up, that means your affinity for your substrate goes down. So your enzyme wants the substrate a little bit less. Now, when the Km goes down, that almost sounds like a positive thing, and a good thing, because when the Km goes down, that means your affinity for your substrate goes up. Now, is that inherently like this is one of the places where it gets kind of complicated, because I personally have a tendency to say, is that good or is that bad? And that's a tough habit to break because I think that it's very natural. Now, with respect to this, with respect to the effectiveness of an uncompetitive inhibitor, well, one thing that's worth noting is that your enzyme has a lower affinity for the substrate, or has a greater affinity for the substrate. But at the end of the day, the important part is what happens to your maximum velocity. It's going down. So that's almost like, well, it almost doesn't matter if your Km goes down, because if your enzyme is going to be binding that substrate, but then it's too going to be binding the inhibitor, then the reaction's not going to take place. Now, I always try to figure out, well, why is this taking place? Well, here's one of the ways that I think about it. Let's say that you have, I'm going to do this as rounds. Round 1, 2, 3, enzyme. And then EIS. Okay. So let's say that when you start this out, you've got 100 copies of the enzyme. And then what's going to happen is all 100 of those are going to bind the substrate. And you're going to form 100 of the ES complexes. Now, this is at the start. Okay. 20 of these, let's say 20 copies of this ES complex, then go on to bind the inhibitor. You end up with 20 of the EIS complexes. So what does that mean for the remaining 80 of the ES complexes? Well, they go on to make 80 products and 80 copies of the free enzyme. Okay. So from round one to round two, what happened to your enzyme concentration? It went down. The amount of enzyme that you had went down between rounds one and round two. Okay, so then all 80 of these will again form the ES complex. Now let's say that 15 of them go on to form the EIS complex. Now we're down to 15 of these. At the start of round three, you've got 65 copies of the free enzyme. Now you're going to have 65 of the ES complex. 20 of these go on to form the EIS complex, and now you're down to 45 copies. Round four, 45 copies of the enzyme. What I'm getting at is every successive round, your amount of free enzyme is going to go down. So effectively, what they're going to be doing is they're going to be in competition for your substrate, which is why your KM is going to go down. So your KM decreasing is almost an illusion that is brought on by the decreased concentration of the ES complex. Because every successive round, you are losing some of that enzyme. When you lose some of that enzyme in every successive round, that means that the ES complex is more likely to form because the amount of substrate or the binding or the affinity for the substrate is going to seemingly be going up. Now, one thing that is illustrated in this next portion is right here, from here to here. What happened? Well, you increase the substrate concentration. That does nothing to this reaction. You can add more substrate, but the formation of this ES is not the problem. Instead, it's what happens to that ES. So you cannot outcompete an uncompetitive inhibitor by adding more and more of the substrate. Because some of that enzyme is going on to form, like be sequestered in this EIS complex. ES is going to form no problem. EIS is the problem. Okay, so what does an uncompetitive or what does a double reciprocal plot for an uncompetitive inhibitor look like? Looks like this. Now, I want you to know that I want you to be able to calculate a Ki for a competitive inhibitor. So I'll give you a couple of different calculations and say, okay, here's two different competitive inhibitors. Which one is stronger? Which one basically you're more or less looking at it as which one causes your KM to go up more? Because a competitive inhibitor, the KM is going to go up. Whichever one causes the KM to go up more is a better competitive inhibitor. All right, now back to the plot for an uncompetitive inhibitor. Like I said, I don't want you to be able to calculate Ki for this. But what I do want you to know and recognize is that in the presence of an inhibitor, what you're going to see is that your y-intercept, so I will write this as y-intercept, goes up. Okay, when that number goes up, your Vmax goes down. Why does your Vmax go down? Well, your Vmax goes down because of the fact that this is a reciprocal value. So this might be 2 and this is 4, but that reflects a reciprocal value. So your Vmax goes down. Now over here, your Km, well, we are getting farther from 0. So in effect, we're going up. But again, that's a reciprocal value. So your Km is going to be going down. These two lines with an uncompetitive inhibitor, your two lines are going to be parallel to one another. Now, in an uncompetitive inhibitor, here's how you calculate the Ki. You can use the y-intercept or the x-intercept with and without the inhibitor present. It's a pretty simple calculation, but that's all there is to it. I don't need you to know that. I'm not going to ask you that sort of question. I will absolutely ask you a question on how to calculate a KM, or sorry, a KI for a competitive inhibitor. Now, the last type of inhibitor is a mixed and a non-competitive inhibitor. A mixed non-competitive inhibitor, well, we've previously just referred to this as a mixed inhibitor. I brought this non-competitive inhibitor language up because it is relevant. Now, with that in mind, non-competitive and uncompetitive are not the same thing. I cannot stress that enough. The inhibitor can bind for a mixed and non-competitive inhibitor. It can bind to both the free enzyme and the ES complex. The affinity of the inhibitor to the two complexes might be different. So you would design an inhibitor, and maybe it has a preference for binding E. Maybe it has a preference for binding ES. If the binding of the inhibitor changes the affinity for the substrate, Km will be changed, and this is referred to as mixed inhibition. Okay, so one way that you could think about this is mixed inhibitor. What can it do? It can bind to E and it can bind to ES. Now, if the X intercept changes, then it is mixed inhibition. Now, the opposite of that is also true. If the X-intercept does not change, then what you have is non-competitive or non-com inhibition. So another way of describing that is if only Vmax is affected, it's a non-competitive inhibitor. Okay, now the graphs for these are kind of tricky because they can appear in a couple of different ways. Okay, so one thing that we want to do, I'm going to draw a graph for mixed inhibition. In mixed inhibition, your X-intercept is going to change, whereas non-competitive inhibition, your X-intercept is not going to change. So I'm going to draw one line. There we go. That red line represents no inhibitor. Now I'm going to get a green line. Oh, that wasn't what I wanted. Eraser. Green. Okay, I got that. This right here, my X-intercept, does not change. So this is non-com. Okay, now you look at that. Let's take a snapshot of my brain. Well, is that different from this? 100%. It absolutely is. Okay. Is that different from this? 100%. I have an intersection of my two lines on the x-axis. This is non-competitive inhibition. Does my y-intercept change? Yes, it does. Okay. This is non-competitive. Only Vmax changes. Okay, now I'm going to erase this and I'm going to draw my graph for mixed inhibition. Got to get the black lines for my X and Y axis. Now I'm going to switch to red for no inhibitor. Okay, now this is where it gets kind of hairy. Okay, so if binding of the inhibitor changes the affinity or the substrate, Km will be changed. called mixed inhibition. Now, I feel like this is definitely terminology that you need to read between the lines. Changes. Okay, well, if $500 is deposited into my bank account, has the balance in my bank account changed? Yes. Okay. Now, if $500 is taken from my bank account, has the balance in my bank account changed? Yes, it has. So that terminology right there changed. This value could go up, it could go down. Now, this is where it gets kind of hairy with respect to mixed inhibition. I'm going to draw a pair of lines that represent mixed inhibition. One of them I'm going to do in green. And yeah, here we go. Plus inhibitor. Okay. With that line that I just drew, does my x-intercept, therefore my km, does it change? It does. It does. Okay, so that's one way that it could be displayed. Now I'm going to draw a line in, let's go with blue. Okay, so now what we've got is, if you can for a moment, ignore the green line, plus inhibitor. Okay, now, does my x-intercept change? Or is my x-intercept of the blue line and the red line, and the red line, are my x-intercepts different? 100%. Did my x-intercept change? Yes, it did. Therefore, this is a type of mixed inhibition. What happened to my Vmax? Does it matter? It does, from a like understanding what this inhibitor does, but from a standpoint of classifying this, it doesn't. Um, what matters is, in a mixed inhibitor, you are going to see your Km change. Your Vmax may or may not change. So I'm going to add this in. Vmax may or may not change. In the two lines that I drew, Vmax does change. I'm going to erase this line, this line, this line. There we go. Then I'm going to go here. Oh, look at that. If this molecule is capable of binding the free enzyme and the enzyme substrate complex, well, that type of inhibition, yeah, that is a type of inhibition that would be mixed, because my Km changed. My Vmax did not change. That's very similar to this graph right here, but what a competitive inhibitor can do only is bind to the free enzyme. Okay, now let's go ahead and proceed from there. Okay, there we go. Here's the different models, like I was saying, about different types of inhibition. Here's mixed. The result with a mixed inhibitor typically is going to see a decrease in Vmax and either an increase or decrease in Km. Like I said, it changes. The effect of a non-competitive inhibitor can only partially be overcome by high concentrations of the substrate. Now, when it comes to calculating and determining what type of inhibition you're looking at, you need to ask the question, what's changing? Is my Vmax, or is my Km, or is my Vmax changing, or are both of them changing? Is only one of them changing? The x-intercept of a mixed inhibitor is fairly complicated, but when Ki of slope is equal to your Ki of your y-intercept, or in other words, the inhibitor has equal affinity for both the E and the ES complex. then the x-intercept converges at one point on the x-axis. This is known as purely non-competitive inhibition, which is what we looked at first. Okay, so inhibition, to put it bluntly, it's a lot. There's a lot to unpack here. And I know that I use that phrase quite often, but that's because it's true. Um, I think the best thing for you to do is understand those different graphs and understand the models. What I would do is I I remember whenever I was a student, what I would do is I would just get like a piece of paper and draw a plot. I would say this right here. What are the labels of my axes? And then here is no inhibitor. And then I'd say, all right, well, what is this? Okay. That chances are is going to be competitive. Whenever I say competitive, or chances are, I just mean like you should anticipate it being competitive. However, be thoughtful of, well, is it one of those mixed inhibitors? It depends on the context of the question. But I would say that this 9 times out of 10 is competitive inhibitor. Now, if we have something like, I gotta go to another page. This right here. Well, where's our intersection? Our intersection is on our x-axis. So that would be purely non-competitive inhibition. Um, knowing how the x and y intercepts change helps you know how the Vmax and Km change. Understanding those graphs and being able to process that information, I would argue, is one of the most important parts about this particular section. Um, in addition to all of that, be able to calculate the Ki for a competitive inhibitor. All right, everyone. I think that about wraps it up. If you got questions, let me know. Other than that, draw those plots. Know those plots backwards and forwards. Know how a line changes. Does that impact the Km or the Vmax? Now, one thing I'll just say as a little bit of an aside is you can look at the slope. For instance, on all of these graphs, you can look at the slope of the line and um, discern something about the Km and the Vmax. But from my experience, it's not necessarily a bad thing, but it wasn't really as effective as if you know how the X and Y intercept changes. And um, that's because that's the key to what you need to know. All right, everyone, have a good one.